In this video, we'll define apparent power and power factor. Apparent power is actually the magnitude of our complex power. It's equal to the average power of a completely resistive load. So if we have a completely resistive load, the average power and the apparent power will be the same. So if we look at an example of we're driving a linear network with a cosine function with frequency omega and a voltage amplitude Vm, then we're going to get a current that's going to be sourced with an amplitude of Im, still frequency of omega, and we'll have this relative phase shift between the current and the voltage depending upon the load. Our average power we can calculate with amplitudes, 1/2 the product of the voltage and current amplitude, times the cosine of the difference of the phase shifts, or we call them the difference of the angles. If we have RMS values, then we can drop the 1/2 factor, and we just end up with the product of the effective voltage and effective current, but we still have the cosine of the difference of these angles. Our apparent power is just the product of the voltage and the current. It doesn't use the cosine of the difference of the angles, and it's this is when we're using RMS values. If you're using amplitudes, it's just 1/2 Vm Im. So what we see then is it's equal to the average power of a completely resistive load, because if we have a resistive load, then the voltage and the current are in phase. So this theta V minus Vi, that's equal to 0, and the cosine of 0 is just equal to 1. So otherwise, we will have a phase difference. So this cosine will yield something between plus and minus -1, but it'll be less than a absolute value of less than 1. So our apparent power is always greater than or equal to the average power. And again, it's equal to the average power when we have a resistive load. The other thing we note here is the unit that we use for apparent power is volt amps. We use the symbol capital VA for volt amp as opposed to a watt, and that's to distinguish it. Although our apparent power and average power, they're dimensionally the same, they're both power, but we use different names for distinction. So we save the use of watt for average power, and we use volt amps for apparent power. Additionally, we need a different symbol. So for apparent power, since it's the magnitude of the complex power, and we use S for complex power, the magnitude of that is just S, or if we write the magnitude of our complex phasor S. Our symbol for average power, of course, is a capital P, and it's the real part of our complex power. So again, our apparent power and our average power, if we're going to write them in terms of their symbols, the magnitude of S is our apparent power. P, our average power, is the magnitude of S times the cosine of the difference of these angles. And again, our different units. The power factor now, this is another important indicator, and it's an indicator by which of the angle. That's the angle by which the current leads the voltage. We saw that apparent power just looks at the voltage and current magnitudes or amplitudes. The power factor is what recognizes the angle, and it's the angle again by which the current leads the voltage that the power factor is considering. So we can consider it also, we can calculate it actually as the ratio of the apparent power to the average power. So our average power, both in amplitude form and in RMS form, our apparent power, just written here in RMS format. Our power factor then is the ratio of the two. So it's our average power P divided by our apparent power, the magnitude of S. So it is what it is the cosine of the difference of these angles, the theta V minus Vi, the voltage phase shift and the current phase shift. So that's our power factor. The power factor angle is just this angle in here. It's the theta V minus Vi. And again, it's the angle which this is wrong. It's the angle by which the current leads the voltage. Theta V minus Phi is going to give us the angle by which the voltage leaves the current. But when we're talking about power factor leading or lagging, we're talking about current leading voltage. So again, in review here, our effective voltage, that's our amplitude divided by square root of 2, and our effective current, our amplitude of the current divided by square root of 2. So if we're working with effective values, our power factor is just is the cosine of theta v minus vi. So it's something between 0 and 1. Although the cosine can go to -1, our angle is going to be within plus or minus 90 degrees. So plus or minus 90 degrees, the cosine function there is always greater than 1, right? Our cosine function between plus and minus 90 degrees, it goes like this and then like this. So there's our -90 and there's our positive 90. So our cosine function is always going to be positive. It's not going to be negative. So we have to, even if we end up with a negative angle, we'll end up with a positive cosine. So our power factor will be between 0 and 1. So if we have a purely resistive load, then our voltage and current are in phase, and our power factor is equal to 1. That can be achieved still if we have an inductance and capacitance, as long as the reactances cancel. For example, if we had, omega naught, so where our omega naught is 1 over square root of LC, and we're operating at that frequency with these two, a series capacitor and inductor. A purely reactive load, then we're going to end up with our theta V minus VI. I'll just substitute in here so it's clear. I've always used theta for voltage and phi for current, but that's going to be plus or minus 90 degrees. The voltage leads, it's going to be plus 90 degrees for an inductor, negative 90 degrees for the capacitor, but the power factor is going to be equal to 0. So that's the range of our power factor between a completely reactive load to a completely resistive load. Typically, we have some combination. So if we had, for example, a power factor of 0.5, then that theta V minus VI, and I'll write those in there again. Whoops, I'll write those in there because to simplify, it's the difference in the current. So it's also the angle of the impedance, right? So that's going to, if power factor is 0.5, the cosine inverse of that could be plus or minus 60 degrees. So it's plus 60 degrees if it's an inductive load. It's negative 60 degrees if it's a capacitive load. But if all we know is that the power factor is equal to 0.5, we need another indicator to tell us whether the angle itself was plus or minus 60 degrees, because typically we'll just talk about the power factor. That's where we go back to. The power factor is the angle by which the current leads the voltage. So we say if our power factor is 0.5 and it's an inductive load, it's lagging because our current lags the voltage for an inductive load, and our power factor is going to be leading 0.5 and leading if we have a negative angle or a capacitive load. So again, we can't just state that our power factor is equal to 0.5. We have to indicate also whether it's leading or lagging. So that's, if we look at our power factor triangle, and this we can relate directly to our impedance triangle, because as we noted that our power factor, that's equal to the cosine of theta V minus Phi. So it's equal to the cosine of theta Z, or the net impedance of the load. We're also going to say that's equal to the cosine of the power factor angle. So we might be, if we're working with power, we're going to be talking about the power factor angle, and if we're working with impedances, that'll be the same as the equivalent impedance angle. So our angle here is here on the triangle. The magnitudes, or our apparent power, or the magnitude of our impedance, is on the hypotenuse. The real part, which is the resistance for impedance, its average power for power, that's on our x-axis. And then if we have an inductive load or a lagging power factor, our triangle is in quadrant 1. If we have a capacitive load, then we have a leading power factor, then our angle is negative, and our triangle is in quadrant 4. So this, key things to remember: power factor leading or power factor lagging. Power factor lagging is if our impedance angle is greater than 0. It's leading if our impedance angle is less than 0. And what we have to also, and we also have that our impedance angle, that's equal to our power factor angle. So this power factor triangle or impedance triangle comes in quite handy. If we know two things on this triangle, we know everything else. So for example, if we know the power factor angle, and we know, then if we know the power factor angle and whether it's leading or lagging, then we know the power factor. But if we know the power factor angle and the average power, then we can determine our apparent power. And we'll also talk about the reactive power.